As promised, back from the break, still looking at the performance issue for MOS. And typically we're going to be looking at switching characteristics. So what we're going to worry about here a little bit is determining things like resistance and capacitance. And fortunately that's relatively easy to do. To determine capacitance, we estimate the area of a given layer. A layer might be metal or polysilicon, and it's typically computational geometry. So it's relatively easy to calculate what these areas look like because they're pretty much all rectangular shapes. So rectangular polygon shapes that are regular. In which case we just multiply the capacitance per unit area, and that'd be tabulated or given for a given technology, and multiply it by the area, and that would depend on the layer, because things like thickness from the between the layers would vary as well. So there is one notable exception to that. That's our diffusion capacitance, and when estimating the capacitance contributed from diffusion region, a sidewall is taken into account. So that's just because it's more like a 3D kind of looking structure than the planar surface. And as a consequence, we estimate the diffusion perimeter, i.e. the linear dimension around the diffusion area, and multiply that by capacitance per unit length. So when we're in doubt, we use dimensional analysis, which is very helpful. We'll be given capacitance per unit area or capacitance per unit length, and then you know what to multiply it by. Here's some of the little bit more details about an MOS transistor and what some of the capacitances would be. So in this case, you might see something like the source, the gate to drain, but for our purposes, the ones that are going to be of most interest to us might be the capacitance associated with the drain, capacitance associated with the gate to substrate, and perhaps the capacitance of the source to the substrate. And that'll depend, of course, if our source is tied to VDD or ground, in which case we wouldn't have to worry about it. So here's just a very simple illustration of a capacitance per unit area. This is just what would look like from top down, let's say a poly layer, and this is a center line, and we just do a cross section here, and we'd see that we basically have something that resembles a capacitor, and we calculate that by the area times the capacitance per unit area. In the case of diffusion, we'd be looking down, seeing this diffusion region, do a center line, and this would be a cross section then, so we can see that yes, we do have a capacitance which would be to the substrate, as well as a sidewall capacitance which we'd have to take into account. So in effect, it's the capacitance of this material would be area times the capacitance per unit area, and the perimeter times the capacitance per unit length. So again, use dimensional analysis when you're in doubt, and you can't go too wrong. This sort of justifies why we do it per unit length. This is our equation for capacitance. Q is equal to CV, and we know what the capacitance is. It's permittivity times the area over the thickness of the capacitor. In which case we could represent this as the permittivity of the oxide layer, which is stuck in there, or I guess down in here, divided by the T-ox, which is the thickness of the oxide layer. This you have no control over, so you sort of group it together, and then we just see now we have a capacitance per unit area, and we just calculate what the area is of that layer. So it would have a width and a length, and multiply it by the capacitance per unit area which would be given for that technology. So that makes the calculation of capacitance very easy. This is a much older technology, but the point is the same. We'd also have to worry about sidewall capacitance for diffusion, in which case, again, just repeating that we're calculating the capacitance of the diffusion region. We get a contribution from the area, and we get a contribution from the sidewall. So it's the capacitance per unit area times the area, capacitance per unit length times the perimeter. So again, very easy calculations to make. The performance issues considered, well, we have a C, so we're going to have to worry about a R. And it's typically the on resistance of the FET that's charging and discharging the load capacitance that is the biggest factor in terms of the performance of an inverter, for example, or a simple gate. But you can also have parasitic resistances of long lines, and it's estimated by a length to width ratio, and as a consequence we end up basically multiplying the length to width ratio by the sheet resistance, which is in ohms per square. You might not have seen that unit before, but it's a convenient unit for an integrated circuit. So the resistance of a square micrometer is the same as the resistance of a square mile, and that's because it still has the same length to width ratio. So here's a couple of examples. I give you this material here. I get you to estimate what the resistance is here. Well, from the in to the out, there's clearly 4 squares in series, so it's 4 squares times the resistance per square. in this particular scenario here, where it's turned on its side, this is the in and this is the out. This looks like 1/4 of a square. Again, it's the length-to-width ratio that we worry about, and we then multiply that 1/4 of a square by the resistance per unit square. If we had a slightly more complicated looking thing, we're still going to be able to estimate what the resistance is from A to B by just calculating the number of squares. 1, 2, 3, 4, 5, 6, 7, 8, 9, approximately 9 ohms if the resistance was 1 ohm per square. And again, this is sort of how you come out with the justification for resistance per square, ohms per square, because you don't have any control over the thickness of the material. It's not something under your control when you're doing layout or anything else, as you would have control over the W and the L. Maybe you're going to want something a little bit more accurate, and in this particular case, let's say 15 ohms per square, you have 1, 2, 3, 4, 5 squares in series, and this corner square would count as sort of a half square. So you'd have 5.5 times RS, which is 82.5 ohms from this point here to that point there. And that thing would be called a rule of thumb or heuristic, and it's just a rough guide to maybe take into account that this shape isn't perfectly 6 squares, but resembles something closer to 5.5 squares. So some of the performance issues again continued. A few points that we've made. RS is the sheet resistance. It's given in ohms per square. It's given the same thickness. A 1 micrometer by 1 micrometer square has the same resistance as a 1 mile by 1 mile square. So here's in-class assignment 5.2. What is the resistance of a football or soccer field end zone to end zone for a given sheet resistance of 1 ohm per square? So in the NFL, these are football, by the way. In the NFL, it's 100 yards by 53.3 yards, and that's going to give you some resistance. In the CFL, it's 110 by 65 yards. This is why in the CFL we have 3 downs, and the Americans in the NFL have 4 downs, because as you'll see from these calculations, our field is a little less resistive. Well, of course, that's all nonsense. So a summary to this point: understand the DC load line of an inverter, understand the transfer characteristics of the inverter, understand that the load a gate sees is primarily capacitive, and that's because you're talking typically to another gate, or you're talking to a metal layer which is routing to another gate, and it looks like a capacitor. So understand how the load capacitance is estimated from the layout, perhaps back annotated from layout, and this gives you a little bit better idea how well that circuit will perform, because you can do a little more detailed simulation if you start knowing some of these parameters, such as the load capacitance. And that also then is going to impact why things are routed in a particular fashion, and why you try to minimize the length of routes. Understand that the R in the RC is primarily the R on of the driving MOSFET. So when the transistor turns on, it effectively has a resistance, and that's the one that sort of dominates the performance. So you charge and discharge a load capacitor through the on resistance of a MOSFET, maybe N-type, maybe P-type. And that brings us again to another break.